Hi, welcome back. So this is lecture 18 in this course, Bayesian Data Analysis for Behavioral Sciences. My name is Himanshu, and topic of today's lecture is how the data and our prior assumptions together determine the posterior distribution. So what we have seen so far is that the posterior distribution of a parameter theta given some data x is the likelihood of that parameter theta, likelihood function given the data, and our prior assumptions about theta divided by a constant marginal likelihood. Right? If you ignore this constant, you can also write it like this. So the posterior is directly proportional to likelihood into prior. What it means is that the posterior is determined by two things: likelihood and the prior. Okay. So the posterior, which tells you what are the true values of the parameter, which values of parameter are more likely, which values are less likely, given the data and the prior assumptions, is determined by two things: the likelihood function and the prior distribution about the parameter. Right? What does it mean? What does it imply? It implies that your posterior distribution or whatever inference, so basically this is the inference you are making about the true value of the parameter, right? So true values of the parameter after seeing the data. So this is the inference you are making about the parameter. So inference about the parameter depends on two things. First, your prior assumption about the parameter of interest. So what do you believe? What are the true likely values of theta? So your prior assumption about the parameter theta, that's one thing. And another thing is likelihood. So likelihood has actually two things. One, your likelihood assumption, that is, what do you assume, what is the distribution, underlying distribution behind this data. So for example, if you assume that x comes from f of theta, so that's your assumption. Okay, so your likelihood function depends on your assumption. So exactly what is the nature of this function that comes from this assumption, and whatever the actual data you are observing, also the data. So it depends on two things: your likelihood assumption and data. Okay, so these three things together determine your posterior distribution. What three things? Your prior assumption about the parameter theta, your likelihood assumption about the data, that what is the underlying process behind the data, and then the data itself. So actually what observations you have, so what you have observed, right? So that will determine as well that what are the likely values of theta, right? Let us see how it actually comes out to be in practice, right? So let us say this graph indicates the prior distribution of a parameter theta. So let's say this is the graph of a prior distribution of theta. Okay, and let's say this is the graph of the likelihood of theta given the data. Okay, so this will be determined by the likelihood function as well as the actual data you have. Okay, so let's say the prior was telling you that there is an uncertainty about the parameter theta such that the median value is somewhere around 0.7, and the values could be anywhere between, let's say, 0.5 and 0.12 or something, right? The likelihood is telling you that the likely value is somewhere around 0.6, the most likely value, and there is a spread between, let's say, 0.5 and 0.65 or something, right? Now, in this situation, your posterior would look something like this. Okay, so the mean value of the posterior, it will be somewhere in between your prior and the likelihood. So let's say somewhere here. So let's say 0.65, and the range could be 0.5 to, let's say, 0.8 or something, right? So in a way, posterior is a compromise between the likelihood and the prior. Okay, but there is a layer to it, which is that this is not exactly the average of likelihood and prior, right? That's not possible because they are being multiplied, right? You are not taking average of likelihood and prior. That doesn't make any sense. We are seeing that the posterior is somewhere between likelihood and prior. So that is right, but it's not exactly just average of those. The idea is this, that your posterior will be influenced by both data, that is the likelihood function, as well as the prior. So your posterior is going to be influenced by both likelihood and the prior. Now, it could be the case that you have a very strict prior. So let's say you have a lot of information from the previous literature about this parameter theta. So let's say rather than having a prior between 0.5 and 0.12, let's say you know from previous literature, you are well informed from the previous literature that the most likely value of theta is strictly between 0.7 and 0.8 and most likely value 0.75, right? So that's a much more informative prior, right? In that case, the posterior will be more influenced by the prior compared to the previous one, because now your prior has less uncertainty. Okay, you have more information in the prior because this spread of the prior distribution is smaller. That means you have more information in the prior. Okay, your prior has less uncertainty, so it will pull the posterior in the direction of the prior. So basically, a posterior will be pulled in the direction of the prior. So it might look like this. Okay. On the other hand, if let's say you have a lot of data, let's say you've collected 300, 400 subjects in a behavioral experiment, then your likelihood would look like this. So it would have much more information. More data you have, more information you would have, right? And in that case, your likelihood will pull the posterior in its direction, and prior would have lesser effect. Okay. So the idea is this, that both prior and likelihood influence the posterior. Okay. But the dominant influence is determined by which one has more information. So if your prior is much more informative, let's say there is a less standard deviation in your prior, it would dominate its influence on the posterior. If your likelihood is very informative, let's say a lot of subjects, lot of data, then it would dominate the posterior. So posterior might look exactly like the likelihood. And that's what happens. So if you have a huge amount of data, right? So let's say a lot of subjects in a behavioral task, then your posterior would look almost like your likelihood. Then prior wouldn't even matter. And that's a good thing actually, because that what that means is that if you have a lot of data, then you are relying on the data to tell you about the true parameter value, right? If you have less data, then you rely more on your prior belief or prior information about the true parameter. In that case, you do not trust data that much, because if less data, it would be noisy, it would have more uncertainty, so you wouldn't rely too much on it. Okay, let us see how it works out in practice. So we will continue with an example that we took in R in the previous lecture, and let us manipulate information in the prior and the likelihood. Let us manipulate the uncertainty in the likelihood and the posterior, and the prior and the likelihood. Okay. So the example that we were taking were of a binomial distribution. So this was the example, that you have some data. Let's say this is the word recognition task. Okay. In this task, people have to recognize whether a given string on a screen is a word or not. So for example, individuals will see a string written on a screen, let's say BKTR, and their task is to press a key recognizing whether it's a meaningful word or a meaningless string, right? So they will press, let's say, left key if it's a meaningless string, right key if it's a meaningful word. Okay, so experiment is like this, and what we are recording is that how many times they give a correct response. So each participant sees, let's say, 50 trials. Okay, and let's say you're doing this experiment on a single experiment who sees 50 such strings, and we are recording how many times they give a correct response. So n is the number of correct response. Okay, and that's what we want to model. Now what you can assume about number of correct responses? Well, here it makes total sense to assume that number of correct responses comes from a binomial distribution with, let's say, sample size 50 and underlying probability of correct response being theta. Okay. So this is the parameter of interest, underlying probability of correct response. Okay. So in the Bayesian framework, we want to estimate true values of this parameter theta. So what is the underlying true probability of giving a correct response in a particular, in each trial, right? That's what we want to estimate. And how do we estimate it? Using, so first we need to define our prior assumptions about the parameter theta. Okay. So let us start with assumptions like this. Let's say A2. So this is our prior assumption about the parameter theta, that theta has a beta distribution with mean somewhere around 0.8 and a lot of variability around that mean. So we have a lot of uncertainty. So this is not a very informative prior. You can call it a weakly informative prior. Okay. So now we have our likelihood assumption and prior assumption, and let's say now you get your data. So what you get is that the participant gives 45 correct responses out of 50 trials. So this is your data. Okay. And let us now build inference from here. Okay. So what I will do first is this. I would need to calculate likelihood, prior and posterior. Okay. How do I do this? So one method is this, that I can create a vector of theta. So you know that theta could be anywhere between 0 and 1. So let me take a lot of values of theta from 0 to 1. How many? That you can decide on your own. Let's say 10,000. You can take even more. Okay. So this is basically equidistant values of theta between 0 and 1. Now for each value of theta, I'm going to calculate its prior density, its likelihood, and then multiply them to get the posterior density for each value of theta. And when I draw the graph of those posterior densities against theta, that will be the graph of posterior distribution, and that will be my posterior distribution, right? So that's the approach I'm going to take here. Right? By the way, this is only one way to calculate your posterior. There are other more efficient ways to compute the posterior, which we will see later on in next week's lecture. Okay. So right now, let us go with this. You have theta, so vector of theta from 0 to 1. Now you calculate likelihood for each value of theta. How do I calculate likelihood? I know my likelihood assumption, which is that a number of correct responses comes from a binomial distribution. So I can use D binom. So D binom will actually evaluate the PMF of a binomial distribution, right? And that's what I want. So it should take my data, which is x equals to 45, as the data size is 50. So data is fixed, so I have given the data. Now theta is a vector, so it will calculate a likelihood for each value of theta given this data, right? So this is how I can calculate the likelihood. Now I can calculate the prior. How do I calculate the prior? The prior distribution is beta distribution, so I can use d beta, which will evaluate the PDF of a beta distribution. So d beta, and I need to calculate this for every theta. So remember, the prior is on theta. So you think of it as theta is coming from a beta distribution with shape parameters 8 and 2. Okay. So you can calculate probability density for each parameter value or for each value of theta. Okay, and that's what we're going to do. Now you can also calculate approximate marginal likelihood by taking mean of likelihood into prior. So this will give you some constant, right? So it's 0.06, which you can then divide prior into likelihood by this constant. So now the posterior will be likelihood into prior divided by marginal likelihood. Okay, so that's your posterior. All right. Yeah. And you can visualize how it looks like. Theta and posterior. This is how it looks like. But what I'm going to do now, I'm going to plot prior, likelihood and posterior on top of each other so that you can compare that where is the posterior is located in this parameter space, where is prior and where is likelihood. Okay, in order to do that, I will use ggplot, okay, so that I can visualize them well. I will create a data frame containing all likelihood prior and posterior. So this data frame would have theta equals to theta, likelihood equals to LKL, right? Prior equals to prior, and then posterior equals to posterior. Okay, so this is my data frame. Yeah. You can also use library reshape to convert it into a long format. That would be actually useful in this case. Now let us plot this. So ggplot, if you want, you can already melt this. So I'm converting this data frame into a long format, okay, where id equals to theta. Let me show you how it looks like. So this will actually look like this. So theta and corresponding so variable likelihood, and variables would have posterior, prior as well, and its value, right? So it would be useful for plotting this in ggplot, right? So let me plot this. So ggplot data frame. On x-axis, I always want the parameter theta, so values of theta, right? On y-axis, I want value from this data frame. So basically value of likelihood, prior and posterior. And I need to group them by variable. Okay. I can also have color equals to variable. That would also help a bit, so that I get different color for likelihood, prior and posterior. Right. Now I'm going to plot all these three in a single plot. How do I do that? So first, I can plot it using geom line. You can also use geom point. You can draw a point plot as well as line plot. It will give actually same result because you have a lot of data points. And then what I'm going to do, just checking the theme and everything. What I'm going to do importantly is that I'm going to plot them on top of each other, right? So I'm going to do the facet trap by variable, and number of column equals to 1. So in a single column. Then I can set up, yeah, that's it's okay. So let us see how it looks like. So there's one more thing I need to do. So I need to free the scales on the y-axis so that I see all the plots clearly, at least the shape. This is because the values of likelihood, prior and posterior, they are on different scale. Okay, so I need to adjust for that. Okay, so now our plot is complete. So let me zoom it so that you can see clearly. Yes. So this is our plot of likelihood, prior and posterior. So the first red one is likelihood, the green one is prior, and the final blue one is the posterior. Okay. So from this plot, it's difficult to tell that which one is actually influencing the posterior, because both the likelihood and the prior, they both are weakly informative. So they both have a lot of uncertainty. You can see the spread of the parameter. So they have a lot of uncertainty. So it's difficult to tell from this. One thing that can help you is, of course, if you restrict the space, let's say between, because you're not going to get any values of theta that are less than, let's say, 0.5. So you can create limits So let's say from 0.6 to maybe 0.5 to 1. Okay, so this would show you only the right half of the plot. Okay, so this is better for visualization. So yeah, the posterior looks very much like the likelihood. Prior does not have much effect because prior is very uninformative. So it's all over the place, right? So the prior wouldn't have much effect on this posterior. So the posterior looks very much like the likelihood. Okay. Let us now manipulate the likelihood and prior a bit, and let's see how it changes our posterior. Okay. So that's what I'm going to do now. So let me do this. How about this prior, rather than being theta 8.2, what if it is 80.20? Okay. So the mean of the prior would remain the same. It's still around 0.8, mean value is 0.8. But now the spread will decrease. So prior becomes more informative. And let's see how it would affect our inference. See, where is prior now? So prior is here, mean value around 0.8. Okay, likelihood is here. Now posterior is pulled towards the prior. Posterior is being pulled towards the prior, right? Because now prior is more informative compared to the likelihood. Likelihood has more spread, prior has lesser spread. So posterior is actually pulled towards the prior. Okay, let's increase it more. Let's say if you make it 800, 200, what will happen now? So prior is even more informative now. And let us see what happens to the posterior. See, your prior says that the value of theta is strictly between, let's say, 0.78 and 0.82. That's a very strict, very informative prior. It contains a lot of information. There is very less uncertainty about the true value of theta compared to the likelihood. That's why the posterior looks very much like the prior. You will see that still the mean value of the posterior is slightly higher than the mean value of the prior. So prior says it's around 0.8, posterior says it's less, slightly more than 0.8. That's because of the likelihood. So although likelihood is uninformative compared to the prior, but it still contains some information. So it will pull the posterior in its direction, but it is not dominant here, right? So the dominating influence is of the prior. Okay, let me try to increase the font size of the legends so that you might be, let's see if you can see them better. Theme, okay. I don't know if it would work. Actually, this is facet title, so okay, fine. Anyway, okay, so let us do something with the data as well. Let's see how it changes. So let me go back to a prior with 80/20, and rather than having 50 trials, let us have 500 trials. And let's say you got 450 correct responses. Let's see what will change now. This is what changes now. Now the likelihood is much more informative compared to the prior. It has less uncertainty compared to the prior. So you see that likelihood is telling you that the likely value of theta is somewhere between 0.85 and 0.95. Prior is telling you that likely value of theta is around 0.8, and I'm not very sure. It could be anywhere between 0.7 and 0.9. So the posterior is pulled towards the likelihood. You see, posterior is very similar to the likelihood, although it has slightly lesser value. So posterior does not tell you that true value is exactly around 0.9. It is around 0.87 or something. Okay? So that's how a posterior is a compromise between the likelihood and the prior. So the dominant one, is the one which has less uncertainty, more information, less spread of the distribution. The dominant one will have more influence on the posterior. Okay. What if both are dominant one? Say something like this. Well, in this case, the likelihood tells you likely values around 0.9, for a prior tells you around 0.8, although prior is slightly more dominating. So posterior is somewhere in between, but slightly towards the prior. Okay. What if data is slightly more, let's say 1000? Now they might have equal influence. Let's see. Oh no, so data actually, okay, needs to be 9000 or 900. Yes, so now you see that your likelihood is around 0.9, prior is around 0.8, your posterior is kind of exactly in between, so it's around 0.85, right? And also the uncertainty in the posterior is lesser than the prior and the likelihood. That's because we are multiplying these two. So this is how the data and your prior assumptions influence the posterior distribution. So the dominant one, the one which has less uncertainty, one which has more information, right, would have a stronger influence on the posterior. Okay. By the way, this is implying nothing for the inference process. You shouldn't take it as that you need to have a control over your prior and likelihood or something. Those things are given. So prior is something you are making some assumption about the parameter, right, and does not harm your inference process. Data is what you have, so it also doesn't harm your inference process. The point of this lecture is just to understand the relationship between prior, likelihood and the posterior. Okay, so do not draw any implications from this, that what kind of prior and likelihood you need, right? That's not important here. Okay, only takeaway point could be this, that if you have good data, let's say you have a lot of subjects and there is less spread, so let's say data is less noisy, then it doesn't matter what kind of prior assumptions you choose, your posterior would look almost same as your likelihood, right? So there is always a utility in having a larger sample size. So when you have a larger sample size, it doesn't matter whether you do frequentist inference or or Bayesian inference, you will get the same result, you will get the same outcome. Okay, because the likelihood looks exactly same as the posterior distribution, and it has less uncertainty, so it would tell you same thing as a point estimate of the parameter would tell you, right? So that's the main point here, and also how more informative prior can affect your inference, and which is a good thing, which is not a bad thing. We will see why. Okay. All right, so this is it from this lecture. In the next lecture we will see in detail that how do we make decision about what kind of prior do we choose, right? So you need some sort of basis to elicit priors for your parameter of interest, right? So that would be the point of the next lecture. All right, thank you very much, and we will meet in the next lecture.